All right, so we are about to do a kind of continuation of what we've been doing with respect to Lewis structures. So, the topic that we're about to get into is known as molecular shapes. And essentially, what we're doing is we're trying to look at a molecule and all of the atoms that comprise that molecule and kind of come up with an idea of, well, if there's one atom here, there's another one here, 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 here. What are the angles that are kind of separating these different atoms from one another? And, how are those going to be impacted if we have like lone pairs of electrons? So that's what we're kind of going to be getting into here to give a little bit more of an illustration as to what that looks like what a molecule looks like. Now, this is something that is really it's a pretty powerful idea because this is sort of like when you get an understanding of this, this is what's used to design drugs that can be used for like cancer therapies and, well, any other sort of therapy for that matter. Um, so that's why this is really a pretty powerful tool because it's it's advancing a field. In addition to that, one thing that's important to understand and appreciate about this is that what we're going to be talking about today is really kind of the next step from looking at and identifying and drawing or visualizing a Lewis structure. So this is kind of how, this particular branch of chemistry kind of evolves and develops. So with that in mind, molecular shapes. Now, when it comes to basically anything and everything with respect to molecular shape, we've got to know about the Lewis structures and the Lewis diagrams of our individual atoms as well as molecules. It's also helpful to remember the number of valence electrons because one of the things that I want you to be able to do is take a formula and put together what is the Lewis structure of it, and then from that Lewis structure say, here's what the shape is, or the likely shape is for that matter. So this is also an important thing that, when you thought about Lewis structures, you gained a sense of, or when we work through Lewis structures, you gain an idea of, oh, okay, well, nitrogen, it brings in five valence electrons. Chances are nitrogen is going to form three bonds and have a lone pair of electrons. So that's why this is kind of an important slide that you know, have a good sense of. Now, here are a total of three different molecules using only four different atoms. Now, hydrogen is found in all of them. Hydrogen loves to share its one electron and basically get an electron or share an electron, so it gets the two electrons. Carbon has four valence electrons and can share them all, and whenever it does, it's going to complete its octet. Nitrogen, by comparison, nitrogen tends to form three bonds and has one lone pair of electrons. And that's illustrated in the above picture of ammonia. Now, I apologize. Our names for these are water, ammonia, and methane. Those are these four different compounds. Okay, so when it comes to a molecular shape, this idea and the visualization of a molecular shape is captured with this right here. Valence, shell, electron, pair, repulsion theory. Okay, that's a pretty complex set of letters or set of words. This is also known as Vesper theory. If you've ever watched any of the James Bond movies, Casino Royale in particular, the love interest of James Bond was a woman by the name of Vesper Lind. Spelled a little bit differently, but nevertheless, Vesper. Okay. Now, whenever you look at that and you're thinking, where do I even begin? I mean, you've got an idea of valence. You know what valence electrons are. Those are our electrons that are farthest out. But I actually want you to kind of think about this word right here, repulsion. Okay. Now, whenever I hear the word repulsion, the first word that I think of, kind of as a continuation of that, is repulsive. Like you know, if I ate, let's see, I'm going to try to think of a really unpleasant food. Um, let's go with, I don't really like pork. So let's say that someone had, you know, pork snout with spinach, honey, and Skittles. And they're like, here, I blended this into a soup. Chances are I'm going to decline that. But if I did ultimately eat it, I would say that was repulsive. Um, Probably say some other things too. But the word repulsion, you're pushing it away, you're repelling it. I suppose I could have just gone with repel as opposed to giving this lengthy explanation of this horrible sounding food. But what I want you to imagine is, what do electrons do to one another? They repel one another. They're they're negatively charged and they're going to repel one another. And that's kind of the important principle behind this Vesper theory. Now, if we look at Vesper theory and we apply a couple of different models. So this shows us the connection between a Lewis structure and the shape of a molecule. If we look on top here, we've got HCN. This is a compound known as cyanic acid. Now, HCN, or cyanic acid, well, the Lewis structure, I'm going to go ahead and give you the opportunity. We're going to build this out. So hydrogen's bringing in one valence electron, carbon's bringing in four, nitrogen's bringing in five. So we've got a total of 10 electrons to draw. Now I'm going to erase all of this, or rewrite where I've written 10 electrons. Say here, 10E. We've got 2, 4, 6, 8, and then the last two electrons are actually as a lone pair on this nitrogen. Now, with that said, when we're looking at the Lewis structure and relating that to a molecular shape, we don't really need to worry so much about this lone pair of electrons that I drew in there. What we're doing is we're trying to look at this molecule shape with respect to our central atom. Oh, I apologize. And so I can erase these lone pairs of electrons, or this lone pair of electrons, because we don't really need it. Now, this molecule is a linear molecule. Even though this is taking place in 360 degrees in 3 dimensions, this hydrogen atom is as far as it can possibly be from that nitrogen. Now, water, by comparison, I mentioned this last time. What do we know about water? Well, it's got two lone pairs of electrons on oxygen. And those lone pairs of electrons, what are they going to do? They're going to fill a bunch of space. Now, I encourage you to look at this PhET simulation, because that PhET simulation really has some great models for basically visualizing a molecule. Now I'm going to work through a couple of them just to show you some examples, and I think these animations are really just great illustrating the points that I would like to make and that are important for you to understand. So let's first look at this model. And this model is going to be, we've got a central atom and two adjacent atoms. Okay, so the purple ball is our adjacent atom. Now you can click on this and kind of rotate it around. What I want to show you is, let's imagine for a moment that we are not curious, not concerned, but let's just imagine this atom where I've drawn an X and this atom where I've drawn a Y. That's supposed to be a Y. It's kind of good. It's all right. Now, if I'm going to go ahead and click on the atom where my X is. And what I'm going to try to do is basically take my molecule. Let's imagine that Let's I mean, heck, I'm trying to do a model of a model. I don't need to do that. What I want to do is I want to fold X over so that it's right on top of Y. But before I do that, I want you to think about some things with me. The one thing that I'd like you to think about is, well, this right here is two electrons. This right here is two electrons. So I've got electrons between my X atom and my purple atom in the middle. And then I've got electrons between my Y atom and my atom in the middle. Now, when I click on X and I drag it towards Y, what's going to happen? The electrons that are between my purple atom and my X atom, what are they going to do? They're going to repel any other electrons. And the only other electrons in this case that I know of, or that are there, are between my purple atom and my Y. So let's click on X and I'm going to move quickly to move it towards the Y. Oh, oh man. As soon as I'm moving the X, Y is moving. And then whenever I stop moving X, well, the Y is going to move just a little bit more, but that's going to put my my X atom and my Y atom 180 degrees away from one another. Okay, so this is an example of a linear molecule. And so we can describe this with the molecular geometry as something that is linear. Now let's go ahead and I want to take this same molecule and modify it ever so slightly. What I'd like to do is I would like to add two lone pairs of electrons. So essentially, I'm making this become similar to water. There's one lone pair of electrons. There's another lone pair of electrons. Okay, I'm going to rotate this. What do you notice about those lone pairs of electrons? Well, they're far away from one another. They're kind of as far away from one another as they possibly can be, while also being far away from those electrons that are making those bonds. So I've got this kind of what looks like a Mickey Mouse sort of situation going on. What I'm going to do is as I move either of the electrons, the other elements or the other atoms and electrons in this molecule, in this visual, they're going to respond accordingly. So I encourage you to use this because not only can you look at models, but you can then go ahead and look at real molecules. So I'm going to click that and let's go with, well, there's water that we just put together. Let's see the model. Oh, not radically different. Then we could look at NH3. Well, it's three hydrogens and a lone pair of electrons. I encourage you to use this, play around with it because it is helpful. It does have some really great illustrations and it also gives you a good way of visualizing, well, how do these different groups repel one another? So this table right here is a table that I want you to know. What do I want you to know about this table? I want you to know how to read it. I want you to understand what it means. Now, whenever we talk about Vesper theory, um, it always makes me think about my freshman year in college. And what it makes me think about is I had a friend who um, he was convinced that he didn't need to do laundry. And I remember speaking with my other friends and him, and we were like, well, why don't you need to do laundry? And he said, well, whenever my clothes get dirty, um, watch this. And so he got a shirt, he put it on a hanger, and then he sprayed it with Axe body spray. And I don't know if that exists anymore, but basically it was really not a very pleasant smelling stuff. So he sprayed it. It's almost like you get Lysol, a cleaning supply, and you spray it on your clothes, and you're like, I smell clean now. See? I smell great. Um, I bring this up because this Vesper theory uses kind of an axe system. And what I mean by that is these letters represent different things. A represents your central atom. X represents your adjacent atoms. And E represents lone pairs of electrons. Okay. What I want to show you is all of these different molecules, all of these different compounds, and all of these different models. And all of these different models can be manipulated to fit this axe system. Okay. So let's just take this model right here. This is an example of a molecule that obviously has a central atom. And I say obviously because every atom or every molecule has a central atom. So I'm going to label this as A, and then I'm going to stop. I know that there's going to be an X that follows. So now I'll go ahead and put the X there. But that X represents my adjacent atoms. So how many adjacent atoms do I have in this model? Well, that would be my number of bonded atoms. And that's 2. And we represent that with a subscript. So AX2. Now, the last one is the number of lone pairs. How many lone pairs of electrons do we have in this? 0. So I'm not going to actually include E. If I did, I would say something like this, AX2E0. But you could just as easily say AX2. Okay. Now, this is an example of a linear molecule, or a molecule that has a shape that is linear. The 2 adjacent atoms are 180 degrees away from one another. This and this, that's 180 degrees. Now, our next kind of group, well, we've got how many domains does this have? What's a domain? Well, a domain is one of 2 things. It is either a bonded atom or a lone pair of electrons. Now, when it comes to number of domains, what we want to do is look at, well, how many lone pairs of electrons and how many bonded atoms? Well, we can say that if a molecule has 3 bonded atoms, we would label it AX3. It has 0 lone pairs of electrons. This is referred to as trigonal planar. What that means is that you have a central atom, which I'm going to go ahead and use an example, B, and then you've got 3 fluorine atoms. Those fluorine atoms they're on the exact same plane. They're exactly 120 degrees away from one another. Here, here to here. Okay. Now, the next example would be AX. Look to our number of bonded atoms, 2E. E indicates that we have at least 1 lone pair of electrons. This is an example of a bent molecule. And you can see right here what that looks like. The farthest that these atoms can be away from one another, or that these electrons can be from one another, is 120 degrees. Now, our last list with number of domains is 4. We can have 4 domains, which means we could have AX4, a central atom, and then 4 adjacent atoms. We could have AX3E. Well, that's 3 adjacent atoms and 1 lone pair of electrons. Now let's pause and think about that. 3 adjacent atoms, 1 lone pair of electrons. Spoiler alert. NH3 fits that billing perfectly. Now, last but not least is, so yeah, our last but not least is AX2E2. That would be an example of a bent molecule. And you know what the degree angle is? It's 109.5 degrees. So that's how far these different atoms are. And you might look at that 109.5 and be like, huh? I don't get that. Well, this is taking into account, sorry, I have to stand back, where these atoms are on the X, Y, and the Z plane. So this is all in 3 dimensions. So what I want you to do is I want you to know this table. Now, the questions that you should expect for this are, I could ask you, what's the molecular shape of CH4? And I don't want to show my hand too much, but I'm going to say CH4. What's the shape of that? Well, you're going to have a couple of different options. And if you're kind of meticulous with this, what you'll do is you'll see that, oh, carbon brings in 4 valence electrons. Each hydrogen brings in 1. So we got 4 valence electrons from hydrogens and then 4 from carbon. We've got 8 electrons. We have no lone pairs of electrons. And what I'd want you to see then is that, oh, well, we've got 4 bonded atoms. This molecule's shape is tetrahedral. That's the sort of question that I want you to be able to answer. So, am I going to ask you what's the molecule shape of this molecule? Yes, I will. But you have the tools and you know how to do that because you're going to work through solving the Lewis structure. And as soon as you solve the Lewis structure, you'll be able to look at this and be like, aha, that's what it is. Now, one thing that we have talked about with respect to this is we have talked also, about Lewis structures. We have talked about not only what does a molecule look like as a Lewis structure, but now we have an idea of what they look like as a, um, what's the shape of a molecule. I want you to also begin considering what we've talked about with respect to bonds and polarity, but applying it to the structure of a molecule. Now, with that in mind, here is an example of a polar molecule. Now, if you remember, we had a couple of different ways to represent the 2 poles of a molecule. We had and if you remember correctly, this dagger here, the kind of handle part of the dagger, that's nearest to the partially positive atom. And then the arrow is pointing towards the partially negative atom. So this is what is known as a bond dipole. So if you've ever heard, or sometimes you might hear this term dipole moment, that's just indicating that this molecule has 2 different poles. Now, when we look at these different molecules, well, these are going to be great model molecules to ask yourself the question, is this a polar molecule or not? And the great thing is that we can classify a bond as being polar or nonpolar based on the electronegativities. But if I showed you this, I actually don't want you to dig into what are the electronegativities of these atoms. Instead, what I want you to do is to look at the shape of the molecule. I'm going to move forward. Both of those molecules would be classified as polar. And a really great question to ask is, well, why? How am I supposed to know that based on not doing the calculation of the polarity of the bonds? Well, the way that you know that is by you look at if the molecule is symmetrical or asymmetric. So if it's symmetric, that means that it is the exact same on both sides. So as an example, Our nonpolar molecule is CO2. See? So there's CO2. And whenever you might look at this and say, like, okay, symmetric, are we going like this? No, we're not. Typically, whenever it comes to symmetry, we're just splitting it right down the middle, vertically. Okay, there's an oxygen on this side with two lone pairs, there's an oxygen on this side with two lone pairs. Okay, cool, that's symmetric. Now, a symmetric molecule, well, that is a nonpolar molecule. So if a molecule has symmetry, it is nonpolar. If a molecule does not have symmetry and it is asymmetric, then it is a polar molecule. So what this means is that if a molecule is asymmetric, if it has different bonded atoms or has at least one lone pair on the central atom. Okay, at least one lone pair on the central atom. Now, I want to bring up an example that we looked at last time, and last time being your last class period. We looked at this molecule SF4. Now, if you remember SF4, well, sulfur, I think we had a total of 34 electrons to draw here. And if I remember the overall structure of this, it was something like this. F, 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 F. Okay, so that's 8 electrons, and then it's 6 around here, so that's 14. 6 around here, that's 20. 6 around here, that's 26. 6 around here, that's 32. So if I were to draw all the electrons surrounding my fluorines, I would get to 32 electrons, and then I would be left with like actually, yeah, a lone pair of electrons out there. Now I bring this one up. I bring up SF4 because it might be tempting to compare something like CH4. If you remember CH4, also known as methane, what did that structure look like? Well, you had a central carbon, H, 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 H. Okay. That's 8 electrons that it had to draw, and those are the 8 electrons that are there. CH4, you might be tempted, oh, SF4, it's the same thing. You might be tempted to do that just by virtue of it having 5 total atoms, but you would not classify them the same. SF4 has a lone pair of electrons, and by having that lone pair of electrons that is an asymmetric molecule, it is a polar molecule. Nonpolar, CH4. Well, think about this as all of these different charges are going in the exact same, or all of these poles are going in the exact same direction. And so effectively what they do is they cancel one another out, which is the exact same thing that we see with CO2. So a nonpolar or a symmetric molecule has the same bonded atoms and does not have a lone pair on the central atom. So use that as your indicator. If you see a lone pair on that central atom, it is going to be polar. Now, here's the last two examples, or the last few examples that I wanted to go through. NH3. We got a lone pair of electrons on our central atom. Did we have 4 atoms surrounding it? No, we don't. But there's one lone pair of electrons. Therefore, this is a polar compound, this NH3. CH3Cl. Ooh, that's a great one, because I just said that CH4 that's non-polar. C, H, 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 H. Oh, but wait, I screwed up. It's not CH4. Instead, it's CH3, Cl. Whenever I throw that Cl out there, what do we know about Cl? And here's an instance where I'm not asking for a specific number. But what do we know about the most electronegative element? What is the most electronegative element? It's fluorine. Okay. Here we've got chlorine. Well, chlorine is in the same row or same column on the periodic table. Column, up and down as a column. And chlorine is pretty similar to fluorine in terms of how it behaves. So chlorine is pretty electronegative. Now, the point of that is, well, chlorine is not hydrogen. So chlorine is not going to be offset by hydrogen. And instead, what we're going to have is basically this chlorine be kind of an electronegative element, so pulling electronic force towards this X. That's what's happening there. Now, our last molecule that I want to talk about, our last nonpolar molecule, is BF3. Wait a minute. Wait a minute. I don't see a lone pair of electrons on that boron. Yeah, you're right. You won't. And the reason that you won't is because that boron, well, that boron doesn't have to reach the octet. It is happy as a clam with 3 bonds. Okay, so these are all things that, let's go ahead and jog back to those molecular shapes. What we're doing is we're answering the question, what's the geometry of any of these compounds? What's the geometry of this right here? What's the geometry of this right here? What's the geometry of BF3? Okay, let's go back a couple of slides and look at this. BF3. Okay. Is it here or is it here? Okay, well, let's see. It can't be here. Could it be here? No, it couldn't be there because we don't have any lone pairs of electrons on that, specifically on that central atom. So that means that we are left with this geometry right here. It's a trigonal planar molecule. What that means whenever you're visualizing this, and actually let me see if this is one of the compounds in our example. Let's see, BF3 should be. Yeah, I knew it would be. I'm going to go ahead and switch your share for a second to show you what I'm getting at here. So here what we have, I'm going to click and drag one. Oh, wait a minute. This is flat, basically no matter what bond angle you take. So there it's flat. I move this up. Now it's flat. Now it's, yeah, the number of different ways in which this molecule can be displayed vary a little bit. So I encourage you to play around with these models and get a sense of what they look like. All right. Well, I hope that was helpful. I need you to, and I think that it's very important that you be able to go from the formula to the Lewis structure to the geometry. Now, the table that I showed you going up to 4 electron domains, that's it. I need you to know the terminology associated with those structures for 2 electron domains, 3 electron domains, and 4 electron domains. Don't go much beyond that, or don't go beyond that. If you want to find that table, yeah, there absolutely are names for basically every level of structure, but those were the ones that I want you to know. If you have an atom with 6 electron domains around it, is that going to be different? Absolutely. Okay, well, that's what I got. I hope you have a good one. Thanks for coming, everyone.